Hi, for this recording, I'm going to show you how to find the basis of the column space of A and the null space of A, where A is the metric representation of a linear transformation. The linear transformation is T of x, y, z equal to y plus z, x plus z, x minus y. Let's look at the solution. From the earlier part, the metric representation of T is given by A equal to 0, 1, 1, 1, 0, minus 1, and 1, 1, 0. Recall that the null space of A is the set of vector x, y, z, where A times x, y, z equal to 0, 0, 0. To find the x, y, z, we're going to solve this equation, and we're going to do it by row operation. Since the right hand side is always 0, we can omit writing 0, 0 all the time now. So given the metric representation, now we're going to find the row reduced form. So what we can do, the first thing we do maybe is interchange the first row and second row, so that the first row I have a leading one. And then what I'm going to do now with this leading one, I'm going to create a 0 below leading one. So I can take the first row times minus 1, then add to the third row. Therefore, the first row remains unchanged, second row remains unchanged, the third row becomes 0, minus 1, minus 1. Then, second row has a leading one now. I'm going to make sure that the entry below leading one is 0. So I can do second row times 1, add to the third row. Then the first row remains unchanged, second row remains unchanged, the third row becomes all 0. Now we have the row reduced form now, as every row has a leading one, and the column contains leading one other than leading one all 0, and the 0 all at the bottom. Now what does this solution tell us? This tells us that if the right hand side is all 0 now, as we omit writing, it means that x plus z is equal to 0, y plus z is equal to 0 under the column of x, y, z, and z has no leading one, so z is free. Therefore, the solution we will obtain now x, y, z is x equal to minus z, y equal to minus z, and z is free. So we pull out the minus z, we get 1, 1, minus 1. So the null space of A, in this case, is all the scalar multiple of 1, 1, minus 1. So you can see x times 1, 1, minus 1, where x is a real number. This will give you a null space of A. And what is the column space of A now? Recall that the column space of A is spanned by the columns of A, but the row reduced form of A, we find that column 3 is equal to column 1 by column 2. By looking at this column 3 here is equal to column 1 plus column 2 add together. Therefore, you can conclude that column space of A is spanned by column 1 and column 2 of A. As this vector 0, 1, 1 and 1, 0, minus 1 are not multiple of each other, so they are linearly independent. So the basis for the column space of A in this case is 0, 1, 1 and 1, 0, minus 1. Whereas the basis for null space of A is they are all multiple of 1, 1, minus 1, so the basis for null space of A is 1, 1, minus 1. Therefore, we can now answer the dimension of null space. Nullity of A is the dimension of null space of A. This is the number of vectors in the basis of null space of A. A basis of null space of A we know is a vector set contain 1, 1, minus 1, and there's only one vector, so the dimension of the null space is 1, so nullity of A is 1. Let's look at the rank of A. This is the dimension of column space of A, or number of vectors in the basis of column space of A, and we know that the basis of column space of A is 0, 1, 1, 1, 0, minus 1. There are two vectors inside there, so the rank of A is 2. That finished the recording.